The world of quantum computing has just experienced a real shakeup. The new quantum processor, Zuchongzhi 3.0, unveiled by China, not only represents a breakthrough in speed, but establishes an entirely new category. This device, based on superconducting technology, can achieve in just minutes what would take a conventional supercomputer more than 6 million years. More than just an incremental improvement, this marks the opening of a new technological frontier. And here's the most astonishing fact. Zuchongzhi 3.0 outperforms Google's Sycamore by a factor of 1 million. But what makes it so revolutionary? How did Chinese scientists manage to reach this inflection point? And more importantly, what are the implications of this development for the future of computing? Let's break down this unprecedented advance. Stay ahead of the curve with the latest in tech. Subscribe to Data Dollar now and never miss an update on the innovations that are shaping the future of business and technology. Join our community. Zuchongzhi 3.0 represents a colossal leap in the global race for quantum supremacy. In 2019, Google made headlines with its Sycamore processor, boasting 53 qubits and capable of executing a specific task in just 200 seconds. A task that would have taken a classical system more than 10,000 years. Today, the new Chinese device not only shatters that record, but demonstrates an advantage equivalent to 6 orders of magnitude above the American processor, becoming an unprecedented benchmark in this emerging field. At its core, Zuchongzhi 3.0 houses 105 superconducting qubits, arranged in a 15x7 configuration, interconnected by 182 couplers that optimize the flow of information between them. Of these, 83 qubits were calibrated and optimized for the main experiment, aiming to maximize operational stability and minimize error rates. These advances enabled the system to successfully execute a complex task, random circuit sampling, achieving a scale and speed never seen before, thereby setting new standards in quantum efficiency. One of the most notable aspects of Zuchongzhi 3.0 is its extremely high operation fidelity. Single qubit gates achieve a fidelity of 99.9%, while 2 qubit gates reach an impressive 99.6%. These levels of precision allow operations to be executed with outstanding accuracy, drastically reducing errors inherent in quantum processing. Although Google's Willow chip, launched at the end of 2024, also features 105 qubits, Zuchongzhi 3.0 has demonstrated considerably superior practical performance in comparative tests. A key element behind this success is the remarkable reduction in errors. Quantum states are extremely sensitive and can lose information due to external interference, a phenomenon known as decoherence. To combat this, the Chinese team employed advanced materials like tin telluride and aluminum, alongside flip chip interconnection technology, enhancing stability and extending the time qubits can maintain their states. Thanks to this, the processor can perform complex operations for longer periods with greater reliability. This advancement is not an isolated case, but a clear sign that the gap between classical and quantum computing is widening rapidly. While Google with Willow, IBM with its Eagle chip, and other Western initiatives continue refining their platforms, China has set a new benchmark that redefines what is understood as quantum advantage. Classical computers are simply no longer capable of competing at this level of performance in the immediate future. The development of Zuchongzhi 3.0 did not come out of nowhere. For years, China has been solidifying its quantum strategy through massive government investments totaling billions of dollars. These funds have been directed not only toward computing, but also toward fields like secure communications and quantum cryptography. Now, this bet is starting to yield tangible results. China is showing that it can not only keep up with the major tech powers, but is also ready to take the lead, with increasingly sophisticated processors that widen the margins of advantage. This new processor fits within a long-term roadmap that includes earlier developments like Zuchongzhi 2.0 and the photonic Jianzhen series systems. While those pioneering efforts focused on demonstrating quantum superiority over classical systems, the new phase of China's strategy is geared toward practical applications. Upcoming goals include breakthroughs in artificial intelligence, materials science, and advanced cryptography. The ultimate objective is to build a fault-tolerant quantum system, capable of solving problems that even the most powerful supercomputers find impossible. Nonetheless, one of the biggest obstacles remains error correction. Even the most advanced systems still exhibit frequent quantum errors due to the inherent fragility of qubits. Google has made significant strides on this front with its Willow chip, using surface code qubits to lower logical error rates. However, China is not far behind. Researchers at the University of Science and Technology of China are already experimenting with qubit architectures that integrate correction mechanisms, and comparable developments from them are expected soon. Beyond the computational domain, China is also leading in quantum communication technologies, a field with the potential to radically transform global cybersecurity. The country has already built the world's largest quantum communication network, including cryptographic satellites like Misius and an extensive terrestrial network of quantum nodes. These achievements could make data interception extremely difficult, laying the groundwork for a new paradigm in digital security with profound geopolitical and military implications. Zuchongzhi 3.0 stands as compelling proof that China is not merely competing, it is defining the course of quantum progress. However, this does not mean we have fully entered the quantum era yet. Although the benchmark results are impressive, there are still many challenges to overcome before large-scale practical applications can be realized. Quantum hardware remains in its early stages, and achieving reliable, large-scale quantum computing will require overcoming considerable technical barriers. For example, the task where Zuchongzhi 3.0 excelled, random circuit sampling, has no direct application to everyday life. It is essentially a test designed to measure a quantum processor's ability to efficiently manipulate random states, rather than solve real-world problems. And while it is fascinating that this system outperforms supercomputers by millions of years in that context, the key question remains whether it can do the same with concrete, real-world challenges. The real challenge lies in translating this computational power into fields like post-quantum cryptography, drug discovery, or new materials design, areas where complexity far exceeds current tests. Even with near-perfect fidelity, decoherence-induced errors remain a significant barrier. This is why companies like IBM, Google, and now China are focused on developing fault-tolerant qubits, although the path toward robust, scalable quantum computing remains fraught with obstacles. The introduction of advanced techniques like surface code encoding, as implemented in the Willow chip, represents a key step forward, but reliable, widely usable quantum computing is still some distance away. The future of this technology will depend not just on hardware, but also on algorithms and software capable of leveraging it. Improvements in coherence times, new forms of error correction, and, above all, real-world applications that justify mass adoption are needed. Many researchers estimate that within 5 to 10 years, quantum computers will begin to tackle real problems in fields such as finance, logistics, artificial intelligence, and materials science. Zuchongzhi 3.0 is a giant step, but we are still far from the final goal. The quantum revolution is on the horizon, but it has not yet arrived. This new chip is not just a technical evolution, it is a clear warning in the global race for quantum dominance. China has demonstrated that it is not just keeping pace, but pushing the boundaries of what was thought possible. Zuchongzhi 3.0 confirms that quantum computing is no longer just an idea for the future. It is happening now. The next decade will be decisive in determining who leads this technological revolution. Will Western investments in error correction and scalable platforms prevail? Or will China's intensive research strategy take them to the top? One thing is certain, the quantum race has become much more intense. Beyond the fierce competition between nations and tech giants, Zuchongzhi 3.0 also raises important ethical and strategic questions. As quantum computing capabilities accelerate, so does the potential to break current encryption systems that secure financial transactions, communications, and national secrets. This could trigger a technological arms race not only to develop quantum processors, but also to create quantum-resistant encryption standards, redefining the very foundations of cybersecurity. Moreover, the emergence of processors like Zuchongzhi 3.0 invites us to rethink the future architecture of information systems. Classical computing will not be replaced overnight, but a hybrid model where quantum and classical processors coexist seems increasingly inevitable. Future infrastructures may rely on classical systems for general tasks and quantum systems for solving specific, highly complex problems. This hybridization could be the bridge leading us from today's digital world into the true quantum era. If you enjoyed the video and would like to continue learning about technology and markets, subscribe to Data Dollar and leave a like. See you next time.